All right, everyone, welcome to Etale Cohomology on November 17th, 2020. Hope you all had a good weekend. Does anyone have any questions about what we've been discussing so far? All right, so we're about to start talking about the Riemann hypothesis. So last time we discussed the rationality of the zeta function, at least for smooth projective varieties. And we'll discuss more about other varieties today and next time. And then I gave you as an exercise the statement that Poincare duality implies the functional equation for the Weil zeta function. So today we're going to start talking about the Riemann hypothesis for real. So let me remind you what that said. So before we get into it, I briefly discussed what I mean by Frobenius last time, but I want to just do a little digression on Frobenii in general, because there's like 4 Frobenii that show up when you do Etale cohomology, and they do different things to cohomology. So I want to discuss them, then tell you which one we actually care about today, and then I'll state the Riemann hypothesis and start doing reductions. Okay, so this is a digression on Frobenii. Okay, so what's the setting? So X is going to be a variety over a finite field. Well, let's say X0 is a variety over a finite field, FQ, and X will be its base change to the algebraic closure, or an algebraic closure of FQ. So we want to understand Frobenii on X, right? That's what we're trying to understand. And the sort of situation where we can use that to count points, which is what we care about, is where we have a Frobenius, which is a morphism over FQ bar. So that's one I described in a sort of complicated way last time. Let me give you a simple description. So first of all, this is called the relative Frobenius. So, well, yeah, let me just start by listing some Frobenii. So first of all, there's the absolute Frobenius. So this is a map from X to X. And what it does is it just sends every function, well, let me do it this way. It sends any function on F to the Q. So that's the absolute Frobenius. This is not a morphism. So this is, I'll just call this Frob absolute. I'll try to distinguish all the Frobenii that show up today with actual subscripts, and then I'll tell you for the rest. I'll pick one for the rest of the talk and tell you which one I'm going to use. So there's the absolute Frobenius. So this is not a morphism over FQ bar. So can anyone tell me why that is? Just to make sure you guys are awake.
You just can't make the community diagram over FQ bar.
Yeah, exactly right. And why is that? Well, it's because like among the functions on X are the constant functions, and we're raising them to the qth power, right? Which, well, on FQ, that's the identity, but on FQ bar, it's not. So this is a morphism over FQ, but not over FQ bar. Okay, so here's a question. So nonetheless, this still does something to Etale cohomology. So Frob abs gives you a map from, for example, H star XQL to H star X, well, Frob abs pullback of QL. But that's just, I mean, you took the pullback of the constant sheaf, so that's the constant sheaf. So what map is this? Any thoughts? So what map is this? Maybe I'll call it Frob star. Anyone? Okay, so the claim, and this is going to seem weird, is that Frob star abs is just the identity map. So why is that? So proof. So here's a subclaim. It's that the map. So we've Frob is a map from X to X, right? So Frob abs is a map from X to X. So it induces a map from the Etale site of X to the Etale site of X. And the claim is that this functor, so this is a map of sites, so it's a functor going the other way. And the claim is that this is naturally isomorphic to the identity. Okay. And if we prove that, then we win, because the identity evidently induces the identity on cohomology by functor. That's part of what being a functor is. Okay, so can anyone help me prove this? What do we have to show? So what is
inverse function?
Yeah,
inverse functor.
Yeah, so we could make an inverse and then well, that would be showing it's an equivalence, right? That's not quite showing. Yeah, so I'm actually trying to show it's naturally isomorphic to the identity functor. So we have to write down a natural isomorphism, right?
Right.
So what does it mean to write down a natural isomorphism between Frob abs and the identity functor? So like, what is the functor from X Etale to X Etale induced by this map Frob abs? So we have this map, which is the absolute Frobenius from X to X. And suppose we have some Etale morphism. So this is an object of the Etale site, U to X. And then this functor sends U to the fiber product, U times X over X, where here this is kind of via the Frobenius map, right? So what do we have to do? We have to show that this fiber product is naturally isomorphic to U over X, right? Does everyone agree with that? So we want that this U cross X over X is naturally isomorphic to U, or it's canonically isomorphic to U. So can anyone give me such a canonical isomorphism? So in other words, we want a map U. We want a map like this, right? That's canonical. And we want it to be over X, which means that this has to be the same map. Let's call this map pi. So this has to be pi. That's what it means for this to be over X. And so how do you make a map to a fiber product?
You want to give a map to U?
Yeah. So can anyone give me a map to U that makes the diagram commute?
You want a Frobenius map?
Yeah. So if you just take the absolute Frobenius on U here, then this becomes the relative Frobenius. This is called Fu over X. Okay, and then the claim is that in this Etale setting, this map is actually an isomorphism. So the exercise, and this uses that U to X was Etale, is that Fu over X is an isomorphism. Okay, so that concludes the proof. So this relative Frobenius gives you a natural isomorphism between absolute Frobenius and the identity. So that's the claim. And then once we show that this map of sites is naturally isomorphic to the identity, the map it induces on cohomology is also the identity. Okay, so this map, absolute Frobenius, is probably not what we're interested in from the purposes of the Weil conjectures, right? Because it does nothing to cohomology. So considering its eigenvalues or its trace is not very interesting, right? Okay, so last time I told you what we cared about was relative Frobenius. So relative Frobenius. So I just described this for U over X, but this makes sense for any base of characteristic P. So here's what it is. And here's, I described it in kind of a fancy way last time, but I'll try to be concrete this time and give you an example. So we have X to spec K to spec FQ bar. This maps to spec FQ bar maps to itself via the absolute Frobenius. And then we take x prime. So let me call this Frob Q. So this x prime is the fiber product. It's the Frobenius twist of x. If x is defined over fq, which it was in our setting, this is canonically isomorphic to x. And I'll explain again. I mean, I explained that last time, but I'll explain again why that's true in a second. Okay, and then again, we have this fiber product. So x still maps to spec fq bar. It also maps to x via the absolute Frobenius. And then we get a relative Frobenius here. This is called fx over k. So this is what I said we were going to talk about, and it is what we'll talk about, but I want to discuss its properties a little bit before we keep moving. So here's a concrete description of it. And you should unwind that this gives you the same thing. So we have x0, which was over fq. And then we have this absolute Frobenius from x0 to x0. So Frob Q. So this just takes every function to the qth power. So this is a morphism over fq, right? Because when you take an element of fq to the qth power, you just get the same element back. Okay, and this relative Frobenius, so fx over k is just this absolute Frobenius on x0. Let me maybe notate it x0 here, base change to k bar. So if we had to fq bar. So we had a morphism over fq. When we base change it to fq bar, we get a morphism over fq bar. So at least that's compatible with the fact that this triangle commutes. But you should check that this is the same map. So let me just give you some example. Excuse me. So some examples, if you take x to be affine space over fq bar, well then absolute Frobenius is just what it is. You take everything to the pth power. Relative Frobenius, it takes, so if we write this as let's write this as spec fq bar t1 through tn. This sends just the ti to the p, and it leaves the constants fixed. Great. Are there any questions about this? Okay, so there's two more Frobenii. So there's the arithmetic and geometric Frobenius. So we'll see in a second that this relative Frobenius is very non-trivial on Etale cohomology. So there's two more Frobenii. So what are those? Well, you can also, instead of acting on the TIs, you can just act on the coefficients. So in other words, you can take Frobenius from fq bar to fq bar, and then take, so this is an invertible map, right? So let me call this, yeah, let me just call this f sub k. And then you can take, so the two more Frobenii are, you can just take f sub k and base change it to your x, or you can take, well, it's an invertible map, so you can take its inverse and base change it to x. And these both give you maps x to x. But what do they do? So this raises kind of the coefficients of polynomials, so raises coefficients to pth powers. And this takes 1 over pth roots. It takes pth roots of coefficients. So for example, in this example of affine space, this one just raises, it does stuff to fq bar, but leaves the t's alone. And same with this. So the first one raises elements of fq bar to the pth power. The other one takes their pth roots. Okay, so these are called the arithmetic and geometric Frobenius. And the observation So the observation is that the absolute Frobenius on X is just the composition of, so what is it? It's just the composition of this sort of arithmetic Frobenius. So that's here I'm denoting this map by Fk times the identity on X. Really, when you base change to X, what I mean is you're taking the fiber product with the identity on X. So it's the composition of this and the relative Frobenius, which after all, I mean, when I gave you this explicit description of it, what did I say you did? I said you take the Frobenius on X naught and then just base change to FQ bar. So why is this the absolute Frobenius? Well, you're taking p powers of the coefficients here, and then you're taking p powers of the variables here, right? So what this tells you is that it tells you that this, this absolute Frobenius is the identity on Etale cohomology. So it tells you that the relative Frobenius and this arithmetic Frobenius act as inverses to each other. On an elliptic cohomology. All right, so this is the digression I wanted to go on. So for the rest of the talk, when I say Frobenius, so from now on, Frobenius will always mean the relative Frobenius, unless I say otherwise. Okay, but the point of this digression, among other things, was to hopefully you now feel a little bit more friendly with this relative Frobenius, which is really quite concrete. All it means is you take variables to the pth power and leave coefficients the same. But this digression at the end, this observation tells us that knowing what this does on elliptic cohomology tells you what all the other ones do, right? So absolute Frobenius does nothing. This thing we're interested in is inverse to the arithmetic Frobenius. And well, what does that mean? It means it does the same thing as the so-called geometric Frobenius, which extracts pth roots. All right. Are there any questions about this digression on Frobenii? Okay, so with that in hand, let me now state the Riemann hypothesis. So the theorem, our goal, which is the Riemann hypothesis, which is again, so X naught will be a smooth projective variety over a finite field FQ, and X will be its base change to FQ bar. So then the theorem is as follows. So then the eigenvalues of now relative Frobenius, Fx over K, acting on the elliptic cohomology. So here, note, this is the cohomology of a variety base change to FQ bar. So this is a variety of an algebraically closed field. So the eigenvalues of this are algebraic numbers, really algebraic integers. And for any embedding of Q adjoin the eigenvalues into C. So let me give the eigenvalues names. Let me call them alpha I. The absolute value of the alpha I is Q to the I over 2. All right. So this is the statement. So another way of saying this is these are algebraic integers, and like if you just put the algebraic integers into C, they have this very special property that all of their Galois conjugates have the same absolute value, and that absolute value is q to the I over 2. All right. Are there any questions about this statement? So this is going to imply this sort of zeta function version of the Riemann hypothesis we discussed at the very beginning of the course using the Lefschetz trace formula. Okay, so let me make a couple remarks. So first of all, one of the reasons I went on this big digression on Frobenii is that the statement is false if you replace, or it at least has to be modified if you replace this with one of the other Frobenii. So for example, if you replace this with the arithmetic Frobenius, which this is an inverse to, well, you won't get algebraic integers anymore. You'll get like 1 over algebraic integers, right? And then also this q to the I over 2 will become a q to the negative I over 2. Which two i's? They're the same. They're the same. Oh, this is alpha j. I see. Thank you, Qingyuan. Does that help? Are those the two i's you mean? So these two i's are the same. Yeah, great. Okay, so yeah. So this is the statement we're going to try to prove. Okay, so maybe just let me remark. So we already know this in a lot of cases. So, example. So in the case of curves, hopefully you've seen this. This is in Hartshorne chapter 4. So if you haven't seen this, you should take a look. And there are a couple different proofs for curves. So the one in Hartshorne uses the Hodge-Index theorem for surfaces. So in particular, it applies the Hodge-Index theorem to the surface C cross C. So another example, and this one is a little easier. So is if HI X QLI, sorry, H2ix QLI is spanned by cycle classes. Then we know our H. For H2I of X QL. Can anyone explain to me why this is? So if you're spanned by cycle classes, you can just like pick a basis of cycle classes, right? And well, how should I say this? Yeah. So after so let me just prove this. So proof. So after so pick a basis of cycle classes of H2I X. So by cycle classes, I just mean cycle, like the classes in cohomology associated to some subvarieties of codimension I, consisting of cycle classes. Okay, so without loss of generality, so just by extending the base field, you can assume that all the cycles are defined over FQ. So why is that? I mean, we're trying to prove that some numbers are algebraic numbers with some absolute value, but that's insensitive to replacing those numbers with a power, right? Like if you have an algebraic integer, if you have a number whose power is an algebraic integer, then it was already an algebraic integer. And if the absolute values of all the conjugates of some power of an algebraic number are the same, then that was true for the original algebraic number. So okay, so we can just extend our base field so all these cycles are actually defined over FQ. So what does that mean? That means that Frobenius, well, what does that mean? It means we have this surjection from codimension I cycles in X to H2I X QLI. So by assumption, this is a surjection. And this is Frobenius equivariant. So if our cycles here are defined, so we've picked some subspace, sorry, when I say surjective, I mean this is when we base change QL. So we picked some subspace here so that this is surjective. This is a subspace spanned by classes that are defined over FQ. So FQ acts trivially here on V. So this implies that Fx over K acts on H2I of X QL of I trivially. But what is H2I of XQL? That's the one we're interested in. That's just H2I of XQL of I twisted by minus I, which implies that Fx over K acts on H2I of XQL via the appropriate, but via the cyclotomic character to the minus ith power. Okay, and now you have to check, well, how does relative Frobenius act on this thing? Well, it acts the way it's supposed to. It acts with eigenvalues of just, all the eigenvalues are now just q to the I, which have absolute value q to the 2i over 2. So this implies the eigenvalues are q to the I, which is q to the 2i over 2, which is what we were trying to prove. Okay, so there's a little subtlety here. So what we showed is when I say the eigenvalues are q to the I, so this is after assuming that the cycle classes are actually defined over FQ. So over our original field, we will get like q to the I times the root of unity. Okay, so this is a very trivial case. Okay, so now let me start talking about how to actually do the general case. Before I do that, are there any questions about this example? Maybe let me give you an example of a variety for which this is true. So if you take a cubic surface, then the cohomology is spanned by cycle classes. So for example, this proves the Riemann hypothesis for cubic surfaces, or the same for projective space, or any other situation you can think of where the cohomology is spanned by cycle classes. Great. Are there any questions before I start talking about reductions for the general case? All right, so let me start talking about some reductions. So there's two reductions I want to explain now. And then I'm going to explain start explaining at least a generalization of the Lefschetz fixed point formula that we're going to need. And then I'll start kind of introducing the main technique, which will be some kind of analysis of families with big monodromy. So this, by the way, I've decided we're going to follow more or less Deleuze's original proof, at least for now. Okay, so the first reduction is we can replace. So these are reductions for the proof of the Riemann hypothesis. You can replace FQ with a finite extension, FQ to the M. So I already kind of explained this in the example, but maybe can someone explain to me why that's okay? So why are we allowed to take a finite extension of our base field? Yeah, so this just raises the eigenvalues to the power of m. So this has the effect. So this is because this has the effect of replacing the relative Frobenius Fx over k with Fx over k to the m, which raises the eigenvalues, which I've been calling alpha j, to the mth power. Okay, but alpha j satisfies the desired properties. If and only if alpha j to the m does. Okay, but replacing q with q to the m. So that's a little exercise. I mean, it's almost it's very easy. Okay, so maybe let me, before moving on, I actually do want to make a remark about this kind of property in the Riemann hypothesis. Like, this is really special, like the fact that that for any embedding of the field generated by your eigenvalues in C, the absolute values are the same. So maybe, can anyone give me an example of an algebraic number which does not have this property? So remark this property that the absolute value of alpha is independent of the embedding Q join alpha into C is very special. So yeah, so can someone give me a non-example? So a number that doesn't have this property.
Wouldn't most algebraic numbers not satisfy this?
Yeah, so give me an example of one.
But not radicals, unfortunately.
Some yeah, so radicals will, so actual like square roots have this property, but it's easy to make examples involving like square roots that don't have this property.
Something like the sum of two radicals or something.
Great, so let's take like 1 plus a square root of 2. Right, and then any embedding, if you take the field generated by this number over Q, any embedding of that into C, well, there's two embeddings into C, right? One sends 1 plus root 2 to like the positive 1 plus root 2, and the other one sends it to 1 minus root 2, right? Those are the two Galois conjugates. And these don't have the same absolute value. One of these has absolute value like 2.4 something, and the other one has absolute value negative 0.4 something, right? Or sorry, it has absolute value 0.4 something. Right? So those two absolute values are not the same. Yeah. I mean, on the other hand, right, so if I'd taken a square root of a negative number here, then the two conjugates would have the same absolute value. So it's a kind of a subtle arithmetic property. And Arvin says, more generally, any algebraic number with only real conjugates. So not quite any one, right? So root 2, for example, is an example of one of these numbers. Right, so it's some,
yeah, I guess square roots of real numbers.
Yeah, that's right. Or yeah, that's right. Or yeah, that's right. I think yeah. So these numbers. So let me make a definition here. So so if absolute value of alpha is independent of the embedding as above, and let's say absolute value of alpha equals some q, we say that, well, actually, let me, q to the I over 2, we say that alpha is a Q-Weil number of weight I. Okay, so this is not totally standard notation. So some people, for example, if I is 1, they just call these Q-Weil numbers. But I find that a little confusing. But in any case, the notation is just motivated by the Weil conjectures. So it's called a Weil number because these are the Weil conjectures, and then this weight is supposed to correspond to cohomological degree, at least for smooth projective varieties. But there's some more general notion of weight that hopefully we'll discuss at the end of the course if we have time. Are there, so this is a special property of an algebraic number being a cube A number. And these numbers are like actually, in my opinion, pretty interesting. Like just from the point of view of algebraic number theory, like not even like from the point of view of the Weil conjectures. All right, so our goal is to show that, so explicitly, our goal now is to show that the eigenvalues of relative Frobenius acting on the ith L-adic cohomology of a variety over a finite field with Q elements are QV numbers of weight I. So that's our restatement of the Riemann hypothesis. And I wanted to make this definition just so that I can use the phrase QV number of weight I. Okay. So we've made one reduction. We've said we can replace our finite field with an extension. We've given a kind of rephrasing of the statement in terms of this definition. So now let's do reduction 2. So this is a sort of very weird idea, which I think was Deligne's. I mean, I don't want to say it was his big insight, because like you'll see later in the proof, there's a lot of like very difficult algebraic geometry that goes into it. But he observed that it's enough to show a much weaker statement. So it's enough to show the following. So theorem that if X is smooth and projective of even dimension, and let's say even dimension 2D, and alpha is an eigenvalue of Frobenius on HD, so the middle cohomology of X with coefficients in QL, then we have Q to the D over 2 minus 1/2 is less than the absolute value of alpha is less than Q to the D over 2 plus 1/2. For all embeddings Q adjoin alpha into C. All right, so let's prove that this implies RH. Okay, so let me just briefly remark on what we've gained here. So first of all, even dimension is a big gain. So that's only half of varieties have even dimension. The big thing we've gained though is that we're not trying to prove an equality of the absolute values. We're just trying to bound the absolute values. So this is it looks, at least a priori, much weaker than the Weil conjectures. Right. All right. So are there any can anyone help me prove this? So the idea is take products. So the idea is to take products. So this is what some people like. I think, for example, Terry Tao calls this kind of trick the tensor product trick. So he has a nice blog post with lots of examples of this kind of trick showing up. So let's take an example. So let's let Y be any smooth and projective variety. And let's take, let's say of dimension n. So n need not be even here. And let's take Y to the 2m. So this variety has dimension equal to 2 times n times m, right? Do you guys agree with this? Okay, so let's look at its middle cohomology. So H NM of Y with coefficients in QL looks like the direct sum over, well, I1 through I2M, such that the sum of the ij's equals NM of the tensor product of Hij, this is now over J, of Y with QL coefficients. Do you guys agree with this? Sorry, this should be a capital M. So this is just the Kunith formula. So before we prove the general case, let's just look at a special case. So a special case is that all the ij's equal to sorry, this should be this should be dimension 2D. This should be in degree 2D. Sorry, I meant the middle cohomology here. Yeah, so here, if we have a variety of dimension 2D, then its cohomology goes up to degree 4D. So we're trying to prove something about the middle cohomology of 2D dimensional varieties. That's in dimension 2D. So here we should be looking at 2NM. Sorry about that. So this is the middle cohomology of a variety of dimension 2NM is in degree 2NM, right? And so this sum should be 2NM. Very sorry about that typo. All right, so let's take the special case where all the ij is equal to n, right? So then this is, so what this tells us is that this tensor power Hn of Y with coefficients in QL to the tensor power 2m lives inside of H2nm of Y to the 2m QL. Do you guys agree with this? Does anyone disagree? Maybe it's a better question. Okay, so the observation now is that this is the middle cohomology of an even dimensional variety. So if we believe the theorem, that tells us that that for any eigenvalue of Frobenius showing up here and hence here, we have this bound. So we get that that q to the, let's see, we're in dimension 2nm. So we're q to the nm minus 1/2 is less than our eigenvalue. Well, here we're interested in eigenvalues here. So we can the ones that show up in the 2mth tensor powers are like monomials in those eigenvalues. So in particular, one monomial is just taking the 2mth power. So we get alpha to the 2m here. And this is less than q to the nm plus 1/2. Right? Okay, and so now taking mth roots, now we get, taking nth roots, or 2mth roots, sorry, we get q to the n over 2 minus 1 over 2m is less than the absolute value of alpha is less than q to the n over 2, sorry, this should be 1 over 4m plus 1 over 4m. Do you guys agree with this? Great, Freddie has given me a thumbs up. Okay, and now taking the limit as m goes to infinity gives that the absolute value of alpha is q to the n over 2. This is what we're trying to prove. Okay, so that was some special case. So we now proved this for middle cohomology of all varieties. So can anyone tell me how to prove it for all cohomology of all varieties? So this implies the answer for middle cohomology of Y. So we already knew it by assumption, well, at least up to this inequality for middle cohomology of even dimensional varieties. We've now done it for all middle cohomology of all dimensional varieties, but now we have to do not just middle cohomology, right? So Jose suggests Poincare. Yeah, so Poincare duality tells us it's enough to do it either in degree above the dimension or degree below the dimension, but we still have to do one of those. Yeah, so okay, so let's write so Poincare duality says it's enough to do this, to do HR of Y QL for R bigger than the dimension. All right, so can anyone suggest a way to do that? Yeah, so yeah, there's a couple different ways to do this. So one way actually would be to do what I think Jose is suggesting, is to cut by a hyperplane and then do some induction on the dimension. So that would work, but it would require some kind of Lefschetz. So this is more or less what we sketched at the end of last time, with where I indicated that we could at least prove that the middle cohomology of hypersurfaces had kind of algebraic eigenvalues showing up, algebraic numbers as eigenvalues showing up. But we actually didn't prove this Lefschetz theorem. So let me give you a softer argument. So the idea is it's to note that HR Y QL to some tensor power, tensor H0 Y QL to some other tensor power lives inside of H AR plus B of Y to the A plus B. Yeah, QL. Okay, and then choosing, now the idea is that choosing A, B appropriately, we can arrange. So here we use that R is big. We can arrange that this is middle cohomology. But Frobenii sets just trivially over here. So the only interesting eigenvalues that show up are in here, and then we can repeat the same argument. So we can repeat the same argument and take the limit as A goes to infinity. Okay. So this is to work out the details, you should try as an exercise. This is actually not the approach that Milne takes, but I mean it's a little bit softer. So I figured I would do it this way. All right. Are there any questions? So we've now reduced ourselves to showing this inequality, well, and to showing that these alphas are actually algebraic numbers, which we need for this inequality to make sense. In fact, yeah, the way I wrote it, it does make sense without algebraic numbers. But yeah. All right. So in order to proceed, so there's, I mean, this is proving this is still highly non-trivial. Like we've made some progress, but this doesn't really help us that much. So in order to proceed, we'll need to reduce to some situations where we're not working with proper varieties. We're not working with smooth varieties. So we need a generalization of Lefschetz, the Lefschetz fixed point formula. Point formula, and we need it in a variety of settings. So we need it for non-complete varieties, so non-proper varieties. So in a little bit, I mean, the reduction will involve taking a family of varieties over a curve, and then analyzing the cohomology of the push forward local system you get on the curve. So that's going to be like typically if you have a family of smooth varieties over a curve, the curve will not be proper. So that will be a non-proper situation. We're going to have to analyze situations with non-constant sheaves. Why is that? Well, we'll have a family of varieties over a curve with a push forward, like the derived push forward of the constant sheaf on top will probably be a local system on the base. It will be a non-constant sheaf on the base in general. And then we're also going to need to understand sheaves of modules over rings like Z mod L to the n Z. Okay, and this one, at least it's not so well. Can anyone tell me what is the problem with formulating a Lefschetz trace formula for sheaves over a ring like this? So does anyone see like why the statement needs some kind of revision? So before we proved something for coefficients in QL. So even if you just took the constant sheaf Z mod L to the NZ, I think there would be some issue. Right. The issue is that if you have a module over this ring, so the cohomology of a module over this ring need not be free, right? So you need some way of like taking the trace of an endomorphism of a module over this ring, which isn't necessarily a free module, and it's not so clear how to do that. Like, what if your module was just like, you know, FL, right? Like, how would you get a trace that lives in this ring? Right. So what we said before actually works fine with FL coefficients, but if your coefficients here are not a field, one needs to think a little bit about what to do. All right. Are there any questions about that? Okay, so I just want to start with the discussion of non-proper varieties. So we'll so just to show you that the statement cannot be maybe as simple as one might hope. So let's suppose U is a smooth variety, and here X is a compactification, and Z is X minus U is the complement. And let me give these inclusions names. So this is the open embedding, I is the closed complement, and this is let's say a smooth proper variety, just for simplicity. Then we had a Geisen sequence, as Jose mentioned, which the way we thought about it is it came from the following exact sequence of sheaves. So if we have let me actually just do QL coefficients here. So this mapped to QL on X. Maybe I'll notate where things are, and then the co-kernel was I lower star of QL on Z. And this gave us a long Z sequence in cohomology, right? So this gave us a sequence which looked like 0 to H0 with compact support of U with coefficients in QL, goes to H0 of X with coefficients in QL, and you could think of this as compactly supported cohomology or not. This goes to, because X is proper, this goes to Z with coefficients in QL, and then continues on to H1, compactly supported of U with coefficients in QL, H1 of X with coefficients in QL, and so on and so forth, right? So what this tells us is that, so suppose we have a Frobenius action on, or not a Frobenius action, sorry, an endomorphism of X such that phi sends U to U and Z to Z. Right? So then we get a phi action on this whole picture. And what we get is that just because if you have an endomorphism of a long exact sequence, this is always the case. we get -1 of the trace of phi star, -1 to the r of the trace of phi star on HR of XQL equals sum of -1 to the r of the trace of phi star on HR compactly supported of UQL plus sum of -1 to the r of the trace of phi star on HR of ZQL, right? So now if Z is smooth and proper, we get that so we can apply the Lefschetz fixed-point formula that we've already proven to X and Z, right? So what do we get? We get the sum of -1 to the r of the trace of phi star on HRC UQL is equal to the number of fixed points of phi on X minus the number of fixed points of phi on Z, sorry, where these numbers are counted with multiplicity. All right. So here's my question for you. So does this equal the number of fixed points of phi on U counted with multiplicity? Any thoughts? So if it did, then we would have a very soft form of the Lefschetz fixed point formula on U, right? So I probably wouldn't be asking the question if the answer was yes, right? So can anyone give me a counterexample maybe? So okay, so the answer is not in general. So let me give you an example, and I think this is a really fun example. So let's set X to be P1, U just to be the standard A1 inside of P1, and Z to be infinity. And I'll take phi to be the map that sends x0, x1 to x0 plus x1, x1. Okay, so this is kind of translation on A1, right? So what's the number of fixed points of phi on U? Anyone? So this is it's just the map Z goes to Z plus 1 on P1. So how many points does this fix on A1?
0.
Yeah, it's just 0. Great. What's the number of fixed points on Z? Well, Z is just a point. So this is 1. Okay, and now here's the million-dollar question. What's the number of fixed points on P1 counted with multiplicity? So Jose, sorry, you typed 1. I didn't see if that was with respect to Z or P1. So what's the number of fixed points on P1 counted with multiplicity?
Oh, is it given by quadric? No, it's, oh, I guess you get an equation, right? So like x1,
Yeah, so what equation?
x1 squared equals 0. Is that the point?
Yeah, that's right. So yeah, you get x1 squared equals 0. That's exactly right. So what's the multiplicity of the set of solutions to that?
2.
Yeah, so you get 2. Okay, and then here's the observation, which is that 2 minus 1 is not equal to 0. Okay, so okay, and we also could have seen this from the Lefschetz fixed point formula. So here one has to do a computation, but basically because this phi is homotopic to the identity, like you can literally, like if you put a t in front of this x, you can literally just move it to the identity. It has to do the same thing on the cohomology of P1 as the identity. And the identity has, well, the trace on H0 is 1 and the trace on H2 is 1, and there's no other cohomology, so you get 2 from the Lefschetz fixed point formula. Okay, so can anyone explain what went wrong here? Like why the number, like why is this equality here not true in this case?
Sorry, can I ask a question?
Yeah.
By counting the multiplicity, it seems like you want to think of the set of fixed points as a scheme or a divisor or something.
That's right. So strictly speaking, if you remember from the statement of the Lefschetz fixed point formula, it was the intersection number of the graph of phi with the diagonal.
Oh, I see. So that's where it gets counted.
Yeah. So in the case of so how do you actually compute that? Well, in the case that intersection is actually a 0-dimensional scheme, it's just the length of that scheme. So if you like the dimension of the space of global functions as a k-vector space. So in this case, we get k join epsilon mod epsilon squared, which has dimension 2.
Cool, thanks.
Okay, so what went wrong here? So the point is that this when you compute multiplicity, so this computing multiplicity on P1 is not the same as computing it on X, as computing it on infinity. So in general, like multiplicity of a fixed point is not something that is preserved under restriction to a closed subscheme. So why is that? Well, in our example here at infinity, this had multiplicity 2, but on z is just a point. It's impossible for anything to have multiplicity 2 on a point. So this tells us that so even though kind of the only fixed points on P1 and z are the same, their multiplicity viewed as fixed points on P1 or viewed as fixed points on z is different. Okay, so what we get, what we get from this P of E is that we get a Lefschetz fixed point formula if and only if the number of fixed points on U plus the number of fixed points on Z counted by with multiplicity equals the number of fixed points on X. And then the same reasoning tells us this is true if and only if for all X and Z phi, so all fixed points on X, the kind of multiplicity of X as a fixed point of, let me write it this way, the multiplicity of X as a fixed point of phi on Z equals the multiplicity on capital X. Great. Okay, so an example where this happens is if phi is Frobenius. This is always okay because all fixed points have multiplicity 1. All right. So what we've proved, so the corollary, well, well, we've only proven this in a special case, but let me just state the general case, and then I'll discuss it in a little bit. So if U is, we've shown that if U is smooth, with smooth compactification and smooth complement, then the number of rational points of U over fq to the n is the sum, -1 to the r, of the trace of relative Frobenius on to the n, or sorry, to the m, on the compactly supported cohomology of U with coefficients in QL. Okay, so these restrictions on smooth on U being smooth and having compactification with smooth complement are like basically never satisfied. Like they're satisfied for open curves, for example, but not in general. But it's not so hard to get from this to the general case. So in fact, the real corollary is that for U arbitrary, so U a variety over FQ. So let's say U0 a variety over FQ, then the number of rational points of U0 FQ to the m equals the sum of -1 to the r of the trace of fx over k to the m. Sorry, this should be U. Both statements should be U on the compactly supported cohomology. And note, this is the cohomology over the algebraic closure. Okay, so how does one do this? One has to do some kind of annoying devisage and induction on the dimension. So what do you have to do? So we know this for points. This corollary implies it for U a curve. Okay, so now how do you do it for a surface? Well, you take, okay, let's assume resolution of singularities. That's a little, we're not allowed to assume that, but let's assume that. So if you assume resolution of singularities, you can find, if U is a surface, you can find a smooth compactification where the complement is singular. But whatever it is, it's built out of curves, and then you can apply induction on the dimension and you win. Okay, so because we don't have resolution of singularities, this approach doesn't quite work, but an analogous argument works, or a slightly more complicated argument works. All right, are there any questions about that? You can also, I mean, we'll discuss the sort of fancier version of Lefschetz in a little bit for non-constant sheaves. I'll start discussing it now. And you could also prove the sort of general situation using that by induction on the dimension. All right. So this was sort of an intro to what happens for non-compact varieties, and we already saw that it's kind of subtle. So what happens for non-constant sheaves? So let's talk about Lefschetz for non-constant sheaves, and I'll just start discussing that. Okay, so first of all, what should the statement even look like? So suppose E is even, let's just say a lease or locally constant QL sheaf on X naught. So given a map from X naught to itself, or really X to itself, let me just make this X for a second. Given a map from X to itself, we get a map from the cohomology of X with coefficients in E to the cohomology of X with coefficients in the pullback of E. Okay, this is like not the kind of thing that you can take the trace of, right? So, okay, so what do we need? So in order to take traces, we need extra structures. So we need, in addition, a map phi sub E from phi star of E to E. Okay, and then we can take this composition. So then we get a map, which people call phi comma phi sub E star from H star X E to the pullback, to the cohomology of the pullback And then we can apply this phi sub e here to get a map back to the cohomology of E. Okay, so we're looking for a kind of a way of understanding the traces of these maps in terms of fixed points of E. So let's also look at what happens if we have a fixed point. So now if x in x is x phi is a fixed point, so then we can look at the stalk of phi star of x of phi star E at x. So in general, the stalk of the pullback is the stalk of E at the image of phi, and well, x is a fixed point, so this is just ex again. Okay, and then this maps. Sorry about that. This maps via phi e to E sub x. Okay, so we get a map like this. Okay, and then the question we can ask. So let's call this map phi sub x. So the question, and this is the sort of thing we would like to understand, is does the sum over x in the fixed points of phi of the traces of these phi x's, which are endomorphisms of the fibers of E, equal to the sum of -1 to the r over r of the trace of these phi E stars acting on, well, it'll actually be on compactly supported cohomology of x with coefficients in E. So this is the kind of thing we're looking for. So this is at least hopefully plausible. So so maybe let me give you an example, and then we'll call it a day and pick up next time discussing the case where phi is Frobenius. So the main example, and this is what always motivates these sorts of questions, is if x is a finite set. So then, so then what happens? So then the left-hand side is just, so we have phi from x to x. And what is a sheaf on this thing? It's just like a vector space. So we have sort of a vector space Ex, which is a QL vector space for each x. And we have a map phi E from E phi of x to Ex for all x. This is the data in the case of a finite set. And then what are we saying? We're saying that the sum over x in the fixed points of the trace of phi x. So let's call this map phi x is equal to the trace of sort of the direct sum of all the phi x's on as a map from direct sum of all the ex's to itself. So this direct sum is just the global sections. Okay, and this is kind of clear. So basically, it's saying that the trace is only the kind of diagonal blocks are contributing to the trace. So proof is that only the diagonal blocks here. So this is a block matrix, if you'd like, and only the diagonal blocks contribute to the trace. So you should check this yourself. So this is like the special case of a finite set that we're trying to generalize. All right, so we're out of time. So I'm going to stop recording. I'll stick around if anyone has any questions for a couple minutes. And thank you all for coming today.